We continue reviewing calculus 2. Use the ratio test to determine if the series converges or diverges. Right, so ratio test over there. So pretty much we take the ratio of the next term divided by this term, or this term divided by the previous term, and take the k go to infinity. And one thing to note that in the ratio test, we're going to put the absolute values in the ratio. Right. So first of all, let's write down what is the term. So a sub n is going to be 4 to the n over n factorial. Right. The ratio test is we take the ratio of the next term divided by this term and take the index goes to infinity, and we just take the ratio with absolute values. Alright. So there's absolute values divide of 4 a sub n plus 1 is where we have n plus 1 into substitute into n, and we have n plus 1 factorial, and then over a sub n. Dividing fraction is multiply reciprocal. So multiply reciprocal n factorial and then 4 to the n. Right, now we're just trying to simplify. The 4 to the n plus 1 is 4 times 4 to the n power, or I will split as follows. Now 4 to the n plus 1 is 4 to the n times 2, 4 to the first. Right? When we multiply two things of the same basis, we add the exponent. That's what we have. N factorial. N plus 1 factorial is starting from n plus 1 and we're going back times n minus 1 and so on all the way back to n. But we're going to stop at n. So n plus 1 factorial is n times 1 times n factorial. And then we have n factorial over 4 to the n power. 4 to the n power cancel out, n factorial cancel out, and we left with 4 on the top and n plus 1 at the bottom. Right? Now as n go to infinity, the bottom is infinity, the top is 4. So finite divided by infinity, so this one is equal to 0. Now the ratio test, it says if it's less than 1, it is convergent. And this ratio is less than 1. So that means the series is convergent by the ratio test. Right, straightforward like that. So when we use the ratio test, usually we use the ratio test when we have the mixture of two of the following. Let's look at the roll rate. Usually when we have the mixture of two of those things, we use the ratio test. Like in this case we have an exponential function and a factorial. Next we have power and exponential. Right, so first we write out what is a sub n, which is n to the 7 over 7 to the n. Right, and then the ratio. Right, first n plus 1, so we have n plus 1 to the 7 power. We do have the whole fraction. N plus 1, substitute into n to the 7 power, and then 7 to the n plus 1, right? This will be that. And then at the bottom, n to the 7 over 7 to the n. Right. Once again, multiply reciprocal, n plus 1 to the 7 over 7 to n plus 1, multiply reciprocal, 7 to the n times n to the 7. Right. N plus 1 to the 7 power, we cannot really split it up, so just going to keep it like that. And then 7 to the n plus 1 is 7 to the n times 7 to the first. And then we have 7 to the n power over n to the 7. See, here we can cancel out 7 to the n power, and we're left with 7 at the bottom, n to the 7 at the bottom. So what we have here is we really don't need the absolute values after this step because all of them being positive because n is positive. So n to the 7 is positive, 7 to the n is positive. We really don't need absolute values after that, after this step. Right, so we have that on the top. The bottom we have 7 to the n to the 7 power. Right, so what is this limit? Well, we cannot really simplify anything. However, as n go to infinity, n plus 1 is also infinity. So remember, we have something like limit if it is n to the 7 plus n to the 6, for example, over 7 to the n to the 7 power. If this is the problem, we only need to take the higher power, right? Because n go to infinity, this one go to infinity a lot faster than that, so we can just neglect that term. Right. So same thing here. We can say it n plus 1, n go to infinity so fast, such we don't really need the 1 there. Right, there's another way to do this. Another way to think of this as I left out the 1 over 7, right? And then both of them under the power of 7. And so the 1 over 7 and the n plus 1 to the n. Once again, when n goes to infinity, n plus 1 is about the same as n. Both of them are infinity. But of course, if we want to write even more details, by the way, 1 over 7 is a constant. We can take it outside of the limit. And here we rewrite that as n over 1 over n, right? So we split n over n is 1, right? So just write like that. So n over n and 1 over n to the 7. Now this one go to a constant, and 1 over n, of course finite, go over infinity, that go to 0. So 1 to the 7 is 1. Notice that if this one go to infinity, we cannot do it this way. It is a constant power. So we have 1 raised to a constant power. It's going to be 1 times 1 over 7. So this is 1 over 7 and which is less than 1. So that's why this is convergent. Right, next, for the ratio test, it will be better when we have the ratio and we have anything to the positive power. So if we move the e to the negative 9n to the bottom, it becomes e to the 9n. It is easy in that form, so we can say a sub n is equal to n factorial over e to the 9 times n. Right, now we find the limit of the ratio. Yeah, the index here we have k or n, doesn't really matter. Just this one we have n. Right. So limit as n goes to infinity, the ratio. Right, so that is n plus 1 factorial e to the 9 n plus 1 over a sub n will be the same thing. Right, once again multiply reciprocal. Right, e to the 9, and if we multiply it out, it will be 9n plus 9. Multiply reciprocal e to the 9n over n factorial. Right, n plus 1 factorial, we will write as n plus 1 times n factorial over e. Here we write e to the 9n, so we can cancel with that. And then times e to the 9. Right, so we can cancel out e to the 9n, n factorial cancel with n factorial. We left with n plus 1 over e to the 9 power. Now as n go to infinity, n plus 1 is infinity, e to the 9 power is a constant. Infinity divided by a constant is still infinity. And so that is greater than 1 by the ratio test. It is divergent. So the series is divergent. Right. Next we have comparison test. So comparison test meaning we compare the series directly with another series. Also usually, which is just comparison test, we call that is the direct comparison test, as opposed to limit comparison test when we use the limit. Alright, now, so when it's like this, so since we're going to compare with something, we're going to write this series as a sub n. right? So the original series A sub n. So now what we compare to? Actually, let's just rewrite this using the power. Seven times n to the 1/2 plus 9 n to the 1/3. Right. So the reason we write the power like that. So here we say the n to the 1/2 has a higher power than that. So if we compare to anything, it's going to compare to n to the 1/2. Right. Now, if we compare to the, now this is, if we use the limit comparison test, that will be easy. We compare to 1 over n to the 1/2. And what is that? So if we compare with n, right, now we take the one with the high power, which is n to the 1/2. If we consider that as a series, now this is divergent. Now if this is divergent, because the p series equal to 1/2, so this is divergent. Now this, when we have something bigger at the bottom, that means the whole thing is less than that. So if we're going to write if we write like that, and that doesn't work. What I mean, it doesn't work is because this one is divergent. If it is less than divergent, we cannot say anything. Direct comparison test is, if it is greater than divergent, it will be divergent, or less than convergent, it will be convergent. So we have to say it in the sense where we look at this and look like it's divergent. So we have to find something that is bigger than that and still divergent. Right. So like I said, this look like it's going to be divergent. Now if we compare with that limit comparison test, that will be easy. Both of them will diverge. Now for this one, if we use direct comparison test, is something less obvious. So we just need to write this one. We need to write that is greater than something. So we need to say this is going to be greater than something, and that something is divergent. So this will be divergent. Right. Now, so how do we do that? Well, this is to the 1/2 power. This is to the 1/3 power. We know that if it's like that, will be the case. Right. Does that work? Let's see. So if I write, like I said, because the way we look at this, we know that's going to be the divergent already. So we're going to write the proof. By the way, on the test, I'm not so picky with this. If you see that where the limit comparison test is clearly better, just go ahead and use that. I'm not very picky with it. Right. So in this case, we just want to use direct comparison test. So we do as follows. So we start with n to the first power. Of course, it's going to be bigger than anything with the lesser power. Right? Especially as n goes to infinity. So this one goes faster to infinity than the other two. Now, if we have the bigger the bottom, then we just divide them from 2. which one is bigger. Now, the bigger the denominator, the smaller the quotient, right? So this one, the bigger denominator will be smaller quotient. The rest is simple. We put the summation into it. We know for sure the series on the left, I can take out the 2. Just have 1 over n. This is the harmonic series, or we say P series with P equal to 1. Now, once again, this one is divergent. P series, P equal to 1. So times 2 is divergent. By direct comparison test, anything greater than divergent is going to be divergent. So the series diverge. This is the direct comparison test. I said if we use the limit comparison test, we compare to this one, and it's a lot easier than to try to write the reasoning here. Right, so that is if we really want to use the direct comparison test, it's going to be like that. So we kind of know the answer already. We kind of know that it's going to be divergent by compared to this. And then we're just going to write the proof using the direct comparison test. It's kind of backward. But that's the question asked. I'm not very picky on that on the test. Right, so now we have this. So we have sine of n times cosine of n. So what is that? Well, what is the sine times cosine? So in general, sine of 2 theta is equal to 2 sine theta cosine theta. So divide by 2 on both sides. So sine theta cosine theta. If we divide by 2 on both sides, is 1/2 sine of 2 theta. Right, so we'll keep that because we might need to use this. Right, so I'm going to write that as 1/2 sine of 2 theta. Now, sine of 2 theta, what is the values of sine of 2 theta? Well, sine of anything is between -1 and 1, right? Now let's go to the direct comparison test. So we do need the term to be positive. Well, the sign could be negative. Right, so we have to do a little bit trickery here. So let's start from the beginning. Sine of anything is between 1 and -1. Right, so that's what we have. Next, we have 1/2. So that not much there. Divide everything by 2. Right, now we want them to be positive. To make them positive, it will be as follows. If sine of 2 theta is between -1/2 and 1/2, we can say it absolute values of sine of, I forgot the 1/2 here. 1/2 sine 2 theta with absolute values, it's going to be less than or equal to 1/2, right? If it is between -1/2 and 1/2, the distance to 0 of course is less than 1/2, right? If we take the point here, go to 0, that distance is less than 1/2. If we have that point go to 0, that distance is less than 1/2. So if the distance is less than 1/2, then we say that the distance is absolute value is less than 1/2. So for this one, if we're going to put the absolute values of the whole thing, right? Now the top is going to be less than equal to 1/2, so we can say this is less than or equal to the top is going to be 1/2, the bottom is still 4 to the n power. We don't really need absolute values here because all of them are positive. And I can take out the 1/2. Now just keep 1/2. So what do we have here? So if we write out as follows, we have 1/2 and then 1 over 4 to the n, right? Take down the 1/2 and then we still have 1 over that. And here we can manufacturally put the n on the top because 1 raised to n power is still 1. Right. Even though the ratio, this should go from 0 to infinity, but this is a geometric series with the ratio is equal to 1/4. If the ratio is between -1 and 1, so we look at the geometric series here. This is a, r is equal to 1/4. So that is convergent. Right? So this series is geometric series, r is between -1 and 1, so that is convergent. So that one is convergent. Now if that one is convergent, anything less than that is convergent, right? So we said this series is convergent. Not just convergent, it is convergent with the absolute values. So we said the original series is absolute convergent. So if it is convergent with an absolute values, it will be convergent without it. So it is absolute convergent. Hence, it is convergent. Without the absolute values. Right. So this requires a lot of things to put together. But usually the direct comparison test is like that. We kind of know the answer already and we're trying to prove it. The limit comparison test, usually it is a better one. We don't know, we just compare to something and then we see what happened. So that's what we have next, is the limit comparison test. Now if we write this, again I write everything as a power. And we let that be a sub n, the first series. Now the second series is what we choose, and whatever we choose is going to be the one with the highest power on the top and the bottom. So limit comparison test, those when we see the problem, pretty obvious. Something like that too. We have more than one term on the top or more than one term at the bottom. What we compare with is just compare to the one that with only the highest term on the top and highest term at the bottom, right? So this is what we're going to compare to. So let the series of b sub n be we can just take the highest power. We can even take out the 8 and the 4, but I said we don't really need that. But if we have it, it's fine. I said we don't really need the 8 and the 4, we just need the power. Right? Now the power cancel 1/2 and 3/2, so that is 8 and 4 as well. 8 divided by 4 is 2, so 2 on top. The bottom is n to the first. By the way, we can write out the 2 if we want to, but this one, it is a p series when p equal to 1. And the 2 on top is constant, doesn't really do anything, so this is divergent. Right, so that's what we got from the get-go. By the way, if we really want to write that as a p series, we can just take the 2 outside like that. That is a p series when p equal to 1, so that is divergent, and divergent times 2 is still divergent. Infinity times 2 is still infinity. So that's what we have. But at the core of the limit comparison test, we have to divide, take the ratio of a sub n over b sub n. As n go to infinity. So this is not a ratio test. The ratio test is we only have one series and we divide consecutive terms. This is 2 different series and we just divide them. So we're going to have that one divided by that one. Of course, we not divide the whole series. We only divide by the term, meaning this term over this term. Right. So divide fraction is multiply reciprocal. So multiply in. That's 8 n to the 1/2 times n to the first. 1/2 plus 1 is 3/2. And then multiply by 2 here. Right. Now we see that as n go to infinity, a to the n to the 3/2 has the highest power. So that go to infinity the fastest. We don't really need the other 2 terms. So this is equal to 1. Alright, so limit comparison test. If it is equal to, if the ratio is between anywhere from 0 to infinity, meaning it is finite. So this is, I'm just going to say it's finite. So that means a sub n and b sub n behave the same. If it is less than 1, that's what it actually in the limit comparison test is. If the limit equal to 1, so behavior of a sub n and b sub n will be the same. So it's finite. We say a sub n and b sub n behave the same. Because of that, b sub n is divergent, so a sub n is divergent as well. So the conclusion is a sub n diverges because they behave the same and b sub n diverges. So does a sub n. Right. So that is limit comparison test. Like I said, limit comparison test, we don't know from the beginning if it is convergent or divergent. We're just going to compare with the highest power. It just happened to be divergent. So we just need to show that the ratios end up being a constant or finite. Then they will behave the same, and one of them divergent. The other one is also divergent. Right. Next, we have to determine the convergent and divergent of this series. Well, what test do we use? Well, this one is rather obvious. When we see -1 raised to any power, that is the big signal that says that is alternating series test, because we have the alternating factor. The alternating factor may be in that form. We have n or n plus 1, n minus 1. Pretty much -1 raised to the index power, maybe plus something, minus something, doesn't really matter. So this is alternating series test. Right? Before that, let's write the alternating factor. Outside, and then we have 1 over 5 n cubed plus 1. Right? Now, this is the alternating factor. Excluding that, we're going to write a sub n is 1 over 5n cubed plus 1. So remember, in the alternating series, a sub k is the one without the alternating factor. Right. Now we're going to check two things for alternating series test. The first one is a sub n is decreasing or non-increasing. Yeah, I'm going to write that in two different things. So this is one meaning is non-increasing, and that one is when the n term go to 0. So we're going to need to check two things. Yeah, because when I put in the table the format of different things, so it's the best that I can put in that form. But alternating series test, we have these two things. It is non-increasing and it is equal to 0. So we're going to check that. Alright, now this one is non-increasing for sure, because as the bottom getting bigger, as n getting bigger, the bottom getting bigger, the whole thing getting smaller. So it is decreasing, right? So we check, because as n increasing, uh, 5n cubed plus 1 also going up. The bottom getting bigger, the whole thing getting smaller. So 1 over 5n plus 1 is decreasing. As n getting bigger. Right, so that check. The second one is also easy to see that a sub n is this. The top is 1, which is constant. The bottom is infinity. Constant divided by infinity, or finite divided by infinity is 0. So that check. So both of them check. We see this series is convergent. Right. Now this one the same thing. And we write the alternating factor separately. what's left is going to be a sub n. So a sub n is that term. Right, and then we check two things. First, is a sub n is non-increasing, and is the limit of the n term goes to 0 as n go to infinity. So we check those two things. Right, the first one is obvious. As n getting bigger, the whole thing getting smaller. So that is decreasing. So is decreasing. Because as n getting bigger. So that check. Because we can also use derivative to say that it is decreasing. Right, now the limit at n go to infinity of 1 over n to the 1 over 4. Same reason as before. The bottom goes to infinity, finite over infinity is 0. So that check. So both of them check. The original series that converges. Yeah. So sometimes I write is convergent or converges. It doesn't matter. That different way. It's just the English language, right? But that's that. Right. Next, I estimate the magnitude of the error involved using the sum of the first 4 terms of the approximate the sum of the entire series. Well, so we're still on the alternating series because we have the alternating factor. Like I said, -1 raised to n plus 1 or n, it doesn't matter. As long as -1 raised to an index power could be plus something, minus something, doesn't matter. Right. But the remainder is going to be less than the next term. So if we want the estimate the sum of the first 4 terms, is going to be s of n, s of 4, that's the first 4 terms. And the estimate between the actual sum, the actual just s is the actual values, minus s of 4, that put absolute values in it. This is called the remainder, and the remainder is less than the next term, in this case n plus 1. Alright, now again, a sub n is the term that is without the alternating factor. So the remainder is less than 1 over, to the n power. And n plus 1 here, if we use 4, it's going to be 4. So a of 5, right? Just sorry. So the error will be no more than a of 5, and that's going to be equal to 2 to the 5th. Okay, so the error here is more than 1 over 2 to the 5th, which is 1 over 32. Right, so that pretty much it. The error will be no more than the next term. The next term is a sub 5, which is 1 over 2 to the 5th, which is 1 over 32. So that pretty much it.